All right, so back to exponential functions. So 2 videos ago, I introduced exponential functions, and what I said is they're functions of this form, a times b to the x, where a and b are numbers, but b has to be greater than 0, and typically it's not equal to 1, and a is any number you want, although typically we choose it not to be equal to 0. And I try to make an argument that there are a lot of connections between exponential functions and linear functions. And a lot of the things that you already know how to do with linear functions, we're going to learn in this section how to do with exponential functions. And then I took this big, long break where we talked about all these different exponent rules and consequences of these rules and these different facts, which a lot of students really struggle with. And you probably had a hard time even watching that video if you watched that video. However, I think it was worth doing because I think it'll be nice to refer back to this. Because what you'll see is that a lot of the stuff that we already know how to do with linear functions that we want to know how to do with exponential functions will be a little bit more challenging. And the challenge will come from the fact that to do that stuff that we want to do, we'll have to be really familiar with all of these exponent rules, which people tend to not be super familiar with. So with that in mind, maybe we could start doing some examples. So here's an exponential function. F of x equals negative 8 times 4 to the x power. And you're like, whoa, negative 8, is that okay? Yeah, that's totally fine. It's just the value of b that can't be a negative number. So just the base that has to be positive. This a that's out in front can be any number you want, although typically we choose it not to be equal to 0. So suppose this is our function, f of x equals negative 8 times 4 to the x. The two main things that you want to be able to do with the function is, if I give you the input, you tell me the output. And if I give you the output, you tell me the input. We saw all of these in the case of linear functions. So for example, if g of x equals 4x minus 8, it's easy enough for me to ask you what g of, I don't know, negative 2 maybe is equal to. And you're like, that's easy. I'm just going to copy this and change the x into a negative 2. So I get 4 times negative 2 minus 8. I get negative 8 minus 8. And you're like, that's 0, right? No, that's not 0. 8 minus 8 is 0. Negative 8 minus 8 more would give you negative 16. I give you the input of negative 2. You tell me that the corresponding output is negative 16. What if we were trying to do that with exponential functions? What if I asked you to evaluate f of negative 2? I'm asking you what comes out of this machine when you put negative 2 into it. You're like, well, that's the exact same thing. All I got to do is copy the blueprint for the function, which instead of having this linear form has this exponential form, and change all of the x's, the input, into negative 2. So I would get negative 8 times 4 to the negative 2 power. But then I'm like, yeah, that's great, but what's that equal to? Right over here, it was really easy to multiply and then subtract to get this output of negative 16. Here, it's a little bit more challenging. But if you were comfortable with the exponent rule video from the last section, you're not too freaked out when you see 4 to the negative 2 power. You remember that that negative number just means the reciprocal of, so it's 1 over 4 squared. And maybe you know that 4 squared is just 4 times 4, so it's negative 8 times 1/16. And when we're multiplying whole numbers times fractions, you can think about this as negative 8 over 1. Most of you won't even write this step, but I'm going to write it this time just to remind you of some algebraic properties. And then you multiply straight across. So negative 8 times 1 gives me negative 8, and 1 times 16 gives me 16. And now I have this fraction that I can reduce. I can cancel out an 8 from the top and the bottom, and I'd be left with negative 1/2. Note that you can put the negative out in front or up in the top. A negative divided by a positive is a negative number, so you can write it either way. The point is just the output of this machine when I put negative 2 in it is negative 1/2, just like the output of this machine when I put negative 2 in it was negative 16. This was a little bit more cumbersome algebraically to get to that output, but it's the same basic idea. With that in mind, maybe you could evaluate these 3 expressions. They're kind of the same question. Instead of putting negative 2 into this machine, we're putting 1/2 or 0 or negative 3/2 into this machine. And it'd be awesome if you could figure out what the corresponding output would be in each of these cases. And the nice thing is you're going to do basically the same steps. You're going to copy this blueprint and just change all of the variables, the x's, into whatever the input is, 1/2 in this case. So all you got to do is evaluate negative 8 times 4 to the 1/2 power, or negative 8 times 4 to the 0 power, or negative 8 times 4 to the negative 3/2 power. And as long as you know what 4 to the 1/2 or 4 to the 0 or 4 to the negative 3/2 is, this isn't that bad. 4 to the 1/2 power from the previous video, that's the square root of 4. And the square root of 4 is just equal to 2. And 2 times negative 8 just leaves me with negative 16. Over here, 4 to the 0 power is equal to 1. So this is just negative 8 times 1. In other words, negative 8. Then over here, probably the hardest one, 4 to the negative 3/2 power. Well, first of all, that negative tells you reciprocal. So we can think about that as 1 over 4 to the 3/2 power. And now maybe I can take care of that fractional exponent. Let's see, 4 to the 3/2 power. The 3 up in the numerator is the power that stays on the 4. And the 2 down in the denominator is telling me to take the square root of that 4. And so I can either write it as 4 to the 3rd power and then take the square root of that. or the square root of 4, and then raise that to the third power. The second way will keep the numbers a little bit smaller, so I'm going to do that, even though either way you'll get the exact same answer. The square root of 4 is just equal to 2, and 2 cubed is equal to 8, so I get negative 8 times 1/8, which you might already know the answer to, but I'm going to do it one more time. I'm going to rewrite that negative 8 as negative 8 over 1, because multiplying a whole number times a fraction is hard, I guess, but multiplying a fraction by a fraction is a little bit easier. You just multiply straight across, you get negative 8 over 8, which you can simplify, and just get negative 1 as the output. If that all makes sense to you, you're kind of halfway there in a sense, because really the goal of this video is to get comfortable with exponential functions when I give you the input, like I did in these 4 cases, but also when I specify the output. If I give you the input, I want you to tell me the output, but if I give you the output, I want you to tell me the input. And these were all things we did with linear functions. So picking on this example again, I could ask you to solve maybe g of x equals negative 16. So here what I'm saying is tell me what the input would have to be so that the output is negative 16. And if you have a good memory, you might be like, wait a minute, I remember when the output was negative 16. That happened when you put negative 2 into this. This answer must be negative 2. And that's true, the answer is negative 2, but pretend you hadn't just done this work. How would you be able to come up with that input of negative 2 that corresponds with this output of negative 16? Well, that's all something that we can do, because g of x, the output, is specified right here. G of x is 4x minus 8. So instead of writing g of x, I could write 4x minus 8 and set that equal to negative 16. The way I think about this is the output equals negative 16, and then if I can solve this equation for x, I will be solving for the input because the x is the input. How do you solve this equation? Well, it's pretty easy because it's linear. Add 8 to both sides of the equation, and you get 4x equals negative 8. And then divide both sides of the equation by 4, and you get x equals negative 2. Oh yeah, I expected x to be equal to negative 2 because I know when I put negative 2 in, negative 16 comes out. So to get negative 16 to come out, of course I put negative 2 in. We can do that same thing on these 4 examples, although it'll be a little bit harder because we're not dealing with linear functions, we're dealing with exponential functions. What I'm saying is I could ask you to solve f of x equals negative 1/2. And if you're clever, you immediately know the answer without doing any work at all by looking at work we've already done on this page. You're like, wait, you want to know what input would make the output negative 1/2? I remember when the output was negative 1/2, that happened in this example. The input was negative 2. So it must be the case that x equals negative 2 is the answer to this question. But again, I want you to pretend we hadn't just done this work. I want you to pretend I just started you out with this, and you'd have to think about how you could solve that. And what you'll see is it's a little bit of a challenge, but at least we have something to fall back on, right? We know how we did this in the linear case, so maybe we can try to emulate that down here in the exponential case. F of x, the output, is equal to negative 8 times 4 to the x power. So what I'm trying to figure out is when does negative 8 times 4 to the x power equal negative 1/2? Well, I got to solve this equation. The problem here is solving exponential equations is really hard, and we won't really become experts at it until the very end of this section. But these specific problems we do have ways to deal with, and I want to show you how. Your goal is to get the exponent all by itself. So this negative 8 is kind of causing trouble here. So I could divide both sides of the equation by negative 8. That's not easy at all, because when you divide by negative 8, you end up with fractions inside fractions, which is kind of hard to deal with. Right? You'd have this negative 1/2 divided by negative 8. There's 2 ways around that. The method that's probably easier, but for whatever reason I never see students do it, is instead of dividing both sides by negative 8, you could multiply both sides by negative 1/8. Because if you multiply both sides by negative 1/8, that negative 1/8 and this negative 8 will cancel each other out, and then you'll just have another negative 1/8 over on this side of the equation. And negative 1/2 times negative 1/8, that's easy, that's just 1/16. The negative times the negative is a positive, and the 2 times the 8 gives me the 6. However, for whatever reason, students hardly ever do that, and what they instead do is write something that kind of looks like this, and I want to make the argument that this is salvageable. What you can do if you have a fraction divided by a whole number is recognize that that's kind of hard, but it's not that hard to do a fraction divided by a fraction. So instead of writing a negative 8 down here, write it as a fraction. The way you write negative 8 as a fraction is as negative 8 divided by 1. And the reason that's beneficial is because there's a method to dividing fractions. The way you divide fractions is you multiply by the reciprocal of the denominator. In other words, you take this guy and you flip it upside down. So I would have negative 1/2 times negative 1/8. You can always change division of fractions into multiplication of fractions by multiplying by the reciprocal of the denominator. Take the bottom, flip it upside down. Note that when you do that, you get exactly what you would have gotten if you multiplied both sides by negative 1/8 to begin with up here. But whatever, one way or another, you get that 4 to the x power is equal to whatever this product is. Well, negative times a negative gives me a positive, and 1/2 times 1/8 gives me 1/16. That was hard, and we're still not done. because we haven't solved for x, we've solved for 4 to the x power. And how do I get rid of this 4? How do I get this x by itself? It's tempting to be like, I don't know, divide by 4 or something. Now, if it was 4 times x, you divide by 4. But this x is up in the exponent, so it's really hard to solve for this x. In fact, to really be able to do that, you're going to have to learn what are called logarithms, which is what we'll get to later in this chapter. But since we haven't gotten there yet, we can't use logarithms. But there is a little bit of a trick, and the trick is to equate the bases. So what I mean by that is I have 4 to the x on the left-hand side. If I could write the right-hand side as 4 raised up to some power, then I'd be able to solve for x. So I'm asking you the question, 4 to what power gives you 1/16? And that's not an easy question at all. However, if you're really good with your different exponent rules from a couple of videos ago, if you're good with these consequences, maybe you can figure that out. Maybe you can recognize that 4 squared gives me 16, but I don't want 16, I want 1/16. But 1/16 is the reciprocal of 16. So what I'm saying is 1/16 can be rewritten as 4 to the negative 2 power. If you have a hard time with that, you can kind of guess and check this side. I think it would be 4 to the negative 2 power. Let's see, what would 4 to the negative 2 power be equal to? Well, the negative would put the 4 down on the bottom, and then 4 squared would give me 16. And I can just tell you from experience that a lot of people will get this wrong. They'll be like, I think it's 1/2, right? But then you can go back and be like, no, 4 to the 1/2 power would be the square root of 4, and the square root of 4 is 2, not 1/16. It's really easy to mess these up, but guess and check the right-hand side, put the exponent that you think is right here, and then use your exponent rules to make sure that that's equal to what you have on the line above. Once we equate the bases like we've done here, it's really easy. Or if we have the same base, if 4 to the x power is the exact same as 4 to the negative 2 power, well, then the x must be the same as the negative 2. Since the bases are the same, if the values of the expressions are the same, the exponents must be the same as well. So x equals negative 2. Wait, what was I doing here? I forgot where this even came from. Oh, right. I was supposed to figure out what input would leave me with negative 1/2 as the output. Remember when we put negative 2 in before, we saw negative 1/2 came out. So this answer kind of checks out. We already knew this would be the answer, but if we had not done this work in red, we would have needed to solve this like we've done in blue. For most people, red's not too bad. For most students, they can kind of pick up red the first time through. For most students, blue is trouble. Blue takes a while to get comfortable with. Before ending this video, I want to get a little bit more practice with this. So what I'm going to do is B, C, and D, except for backwards. So the answers that we got in B, C, and D, the outputs were negative 16, negative 8, and negative 1 respectively. And what I want to figure out is if I were told those outputs, what would the input be equal to? And I know the answers better end up being 1/2, 0, or negative 3/2, or else I made some sort of mistake. But I want to pretend that I haven't done the work in red and I just have the work in blue and see if I can figure this out. The steps will be pretty similar to what we did over here. In each case, we're being told the output. So what we want to do is take the output of the function, this negative 8 times 4 to the x power, and set that equal to these values. And that leaves me with these 3 equations, and I just have to solve these 3 equations. And the way I'm going to solve them will be kind of the same way I did it up here. First, I'm going to get rid of this negative 8. First, I'm going to isolate the exponent here. So to get the negative 8 out of here, I want to divide both sides by negative 8. That'll give me 4x equals 2 here because a negative divided by a negative is a positive, and 16 divided by 8 gives me 2. Over here, negative 8 divided by negative 8 would give me 1. So I got 4x equals 1. And over here, negative 1 divided by negative 8 would give me positive 1/8. So I'd get 4 to the x power equals positive 1/8. Now I'm at the step where the 4 to the x is isolated, kind of like I was right here. And now what I have to do, because I don't know logarithms yet, but soon enough we will know them, is this little trick where I equate the bases. So I have to write the other side of the equation so that it has the same base as this does over here. And sometimes that's easy and sometimes that's hard. Over here, you have to ask yourself the question, 4 raised up to what power would be equal to 2? Well, let's see, 2 is the square root of 4, so 4 to the 1/2 power would be equal to 2. So I can rewrite this 2 as 4 to the 1/2 power. The advantage to rewriting this 2 as 4 to the 1/2 power is now I have the same base. And if the bases are the same and the values are the same, then the exponents have to be the same. X must be equal to 1/2. Similarly over here, if I wanted to write 1 as 4 raised up to some power, my question to you is what would that power have to be? Well, maybe you remember from our exponent consequences a couple videos ago that 4 to the 0 power is equal to 1. So 4 to the x equals 4 to the 0, that implies that x is equal to 0. This one is especially challenging, but I think there's one on the homework that's kind of like this, so I want to show you how you can do it. The goal here is the same. It's to write 1/8 as 4 raised up to some power, but the problem is that's really hard. It's really hard to figure out what power you have to raise 4 up to make it equal to 1/8. If you could figure that out, great. I mean, we kind of know what the answer is going to be because we've already done this work in red. But if you hadn't done this work in red and could figure that out, that's really impressive. But I think for most people, you can't. But you might recognize that both this 4 and this 1/8 can be rewritten with the base of 2. 4 is just 2 squared. So I could think about the left-hand side of the equation as 2 squared to the x power. And 8 is 2 cubed, so I could think about the right-hand side of the equation as 2 to the negative third power. The negative puts it down in the reciprocal, and 2 cubed gives me this 8. The advantage to writing it this way is I'm only one step away from writing this with the same bases. That base is not a 4. That base is going to end up being a 2. But that's fine. As long as I end up with the same bases, I can say that the exponents are the same. The problem is this one's 2 squared. It's not just 2, it's 2 squared. But you have this exponent rule. It's your third exponent rule. This says when you're raising exponents to exponents, you can just multiply those two exponents. So we can rewrite 2 squared to the x power as 2 raised up to whatever 2 times x is equal to. Well, 2 times x is 2 times x. So the left-hand side of the equation is 2 to the 2x power. The right-hand side of the equation is 2 to the negative 3 power. So what I now have are two expressions that are equal, and they have the same base. And if their bases are equal, then their exponents have to be equal. So 2x must be equal to 3, and therefore x must be equal to negative 3 halves. Oh, right, I knew it was going to be negative 3 halves because when I put negative 3 halves into this machine, negative 1 came out. So, of course, the thing that I will have to put in to make negative 1 come out is this negative 3 halves. One last comment that I want to make before I end this video. These all seem to work out that I could write the thing in the right-hand side of the equation with the base that's on the left-hand side of the equation. But that's not something that's always possible. That's just something that will be possible in this section. In future sections, we'll learn what to do when that's not the case.